Yeah, well, and thank you for actually inviting me to talk here. It's very nice honor. And I want to start to just remind ourselves, like mantle convection. Mantle convection is the main process that drives the Earth, the Earth mantle, and understanding it's a crucial for our knowledge of the Earth's past. Its interaction with the surface, it's one of the few ways that we have to actually observe it and studying it. It affects the surface of the Earth, creating horizontal and vertical motion. And this is due to hot and cold anomalies transiting through the mantle. The horizontal motion, usually it is expressed using plate tectonics. So how fast or how slow the plates move towards or far away from each other. The vertical motion, it's expressed through uplift and subsidence of the surface. And this can be due to hot material like a plume rising through, or cold material like a slab transiting, sinking down in the mantle. The mantle, it's mainly made out of silicates, and this creates, it's very highly viscous, so which creates a very slow convection, which is in the time scales of millions of years, which we also call geological series. It is a simple way to study it because it's very highly viscous. It means that we can neglect the inertial forces, and we can do the approximation of the Stokes flow. This means that the Rayleigh number is very, very small, and the flow is instantaneous and linear. This implies that the flow it's entirely defined by how the boundary conditions are at any moment in time. So at any changes in forces in the fluid around it, this will affect, there was going to be an instantaneous balance of the forces in. That means that viable mountain flows must be computed in a global geometry, because if we choose another type of geometry, the boundary conditions will affect highly the fluid, and this will create not a representative way of showing mantle convection. Solving the Stokes flow gives us a way to understand how different quantities in the surface of the Earth can we can observe it. So how, for example, the geoid undulations, the gravity anomaly of the surface topographies can change while we apply different Earth models. So for example, here it's complicated, but I just want you to see that if we choose different viscosity profiles in that sense, so the upper row or in the lower row, if we have a layered mantle, the surface impact of different quantities will change how we see it. And because my work is mainly focusing on how we see surface topography due to mantle convection, we can just look at this highlighted row. So what these tell us, it's our, what in seismology we would call the green functions. It tells us, given a size of an anomaly and a position in the mantle, how this will affect the surface of the Earth. So for example, we can put ourselves in a spherical harmonic degree 2, which means that it's around 10,000 kilometers. And if we locate ourselves here in the middle of the mantle, which this means this point in here, in a isoviscous profile, we see that the contribution is this bluish color, which means that there's a contribution in the surface. But if we go to the layered case and we locate ourselves in the same type of a wavelength, but in the same place in the mantle, we see that the contribution is much less. And even if we can go even to a spherical harmonic degree higher, which meant, for example, a spherical harmonic degree 10, which means it's around 1,000 kilometers, and we would be located around here. And if you can see, is that the contribution in this case, it's actually null, when in here we will still have some contribution. So this show us that different profiles of different profiles of viscosity will give us a different idea of how the surface is impacted. So from here, we learned that, yeah, if we change it, we will see something different. So what we can do now is go back in time, well, go in time. And what I present you here is actually a movie that I have. Yeah, hopefully you can see it in Zoom also. So what you see here is a standard geodynamic Earth model, and it represents the acquired knowledge in geodynamics for the last 30 years. What you see is 4 points of view of the Earth. So this standard Earth model is the result of solving computationally the mass, the momentum, and conservation and energy equations, and assimilating the plate surface at the top boundary in the surface as a boundary condition. So this implies that the continents are not moving at constant velocity far away from each other. Sometimes they will go faster and sometimes they will go slower. And this will reflect in that the flow will be dominated by how this condition is applied. The simulation started 200 million years ago, and it will finish at present day. Cold downwellings known as slabs and hot upwellings known as plumes are expressed here with the colors blue and red, respectively. The spatial resolution of this model is quite high. It's about 18 million grid points, which is roughly 30 kilometers in the surface. So for example, from here to Sydney until the Blue Mountains, we would have at least 3 grid points. And such resolution actually allows us to adequately model the properties of the asthenosphere in a realistic way and give us, for example, the vertical motion as an output. So I'm going to run it again so you can actually see, well, familiarize a little bit with it, but what I want you to see is that the mantle, for example, under the Pacific, it's much different than the mantle under North America. And even though this is a standard Earth model and the only constraint that we put is the surface velocities, there's some zero features emerging. So for example, the plume here rising in the middle of the Pacific, the slab creating under Asia. We can use also a plume, the Iceland plume arriving here under Europe. And if you look at here, at some point you'll see also the plume rising under the North Atlantic. And there's some subduction zones associated with mountain ranges such as the Andes or the Himalayas that also pop up in this model. So what does this model do for us? Well, it alerts us of the observations that we need to look for. It's a tool to understand which better observations can we find to actually constrain these models a little bit better. So let's go to the presentation again. Yeah, so let's turn to observations. So this is the plate tectonic configuration of the Earth, which I'm probably you have seen millions of times. We can identify, for example, the Pacific plate or the Australian plate, African plate here. And even though you have seen that before, what we can do now is take a little bit of a modern approach and see what we learned in the last years. We can plot, for example, in the plate configuration that we have now, the surface, the spreading rates. And so the spreading rate is the velocity at which the plates move away from each other. And this slide shows you the motion of the plates throughout time. The colors represent the magnitudes of the plates, of the spreading rates. And we designed specifically this color scale to highlight the changes in the Atlantic and the Indic realm. So, for example, this brownish purple-ish means very slow velocities. And if we go to this greenish, bluish type, it's a little bit faster. Because there's quite a lot to observe in here. And we see that actually the plate tectonic velocities change quite a lot. What we extracted is some profiles throughout the Indic and the Atlantic realm. In the y-axis, we plot the spreading rate velocities in centimeters per year. And in the x-axis, there's the time in millions of years. And if we look now, we can look at some iconic features. So for example, if we look at the North Atlantic, we see that we have the initiation of a spreading rate at around 60 million years with high velocities during 10 million years and then a drop. We can also see the bimodal behavior of the spreading rates in the South Atlantic, which we can see here amplified. And what we see is that they were high in the Mesozoic, so usually between 100 to 80 million years. Then they drop down for 10 million years, and then they speed up again and again until the Oligocene, which is around 30 million years. These observations have been known since the early days of plate tectonics. It's nothing new. And even though we have pictures in textbooks that says that the Earth has smooth process, what we see is that actually the plates change fast in time. Sometimes they go slower, sometimes they go faster. They are not always constant. And the variation that we see is around tens of millions of years. A mechanism that has been usually built to explain such velocities is plate boundary forces due to to explain this variation, it's plate boundary forces. So, for example, change of stresses due to alpine flow lesion in Europe, or the growth of the Andes in South America. However, another obvious explanation is basal forces due to mantle convection. And this is what I explore mainly in this talk. But mantle convection is very complicated, as you saw in the movie before. So to simplify the process, we can look at conceptual models known as Couette and Poisson. And they are a simpler way to study flow in the uppermost part of the mantle, what we call the Asthenosphere. This view has been popularized over the last decade by Adrian Donardi in Rice University in Houston. So first we have the Couette flow. This flow is created by a gradient of velocities between the top and the bottom of the Asthenosphere. In the case of the Earth, the lithosphere moves on top with certain velocity and drags the material with this linear profile you can see here. This flow is generated usually by the motion of the plates. Then we have the Poisson flow. The Poisson flow is a flow created by lateral pressure variations within the channel. Here, what we have is high pressure on the left and low pressure on the right, and the fluid will move, creating this velocity profile with the maximum velocities in the middle. This can be induced by a plume or a slab transiting through the Asthenosphere. And finally, what we usually encounter is the combined flow, which is a superposition of the Couette and the Poisson. This Couette-Poisson flow model makes an explicit prediction in vertical motion. Every time that the basal forces changes, not only the spreading rate change, but also the topography must change as well. So in other words, there is vertical motion of the lithosphere implied by these models. And recently, well, in the last 10 years, we've become very good at modeling dynamic topography. The group in Cambridge actually has obtained the best residual dynamic topography map in the oceans, with more than 2,000 spot measurements, even more now, of residual bathymetry in the oceanic realm. To extract such a signal, one needs to understand the expected ocean depth and extract systematically the variations from it. There are kind of a lot of different important features in this map. I'm going to highlight here in south of Australia, the Antarctic Australian discordance that has a negative residual topography, or contrary in the North Atlantic on Iceland, on top of Iceland, we have a positive dynamic topography, residual dynamic topography. This has become very useful, but we just have a snapshot in time. But the transient nature of dynamic topography allow us to also go back to the continents and extract this signal. So what we can do is go to the geological record, which has a lot of information of geodynamic processes that has happened. However, I am a geophysicist/geodynamicist, and reading a geological map with the purpose of extracting what happened in the past or which geodynamic processes it's very challenging. And this is because the color scale used. The color scale used, it's mainly, it was designed to amplify maximum the contrast between two layers. So probably you have seen that also at some point. And the color this is the color scheme used for the geological maps. You have pinkish for very old rocks, and then we can go to green, brown for middle-aged rocks, and the very young rocks are expressed with yellow. So if we know more or less that, and we go back to the geological map, what we can see is that, for example, here in South Australia, you have a lot of pinkish rocks, which are very old, but they are in contact with something very, very young. So if we know a little bit about the geodynamic processes, this can be an indication that something has happened in there. So this, recently this data set has been digitalized, and it's possible now for us to determine them. So the only question that we need to solve is, how is vertical motion reflected in the geological record? Well, as I told you before, mantle convection affects the surface of the Earth, and this also affects how sedimentation, occurs around the Earth. Obviously, the real process it's much more complicated, but what I present you here, it's a conceptual model based on what Friedrich et al. Published a few years back. So what you have here is a rising plume, two stratigraphic columns, one on the center of the plume and the other one in the far field. And here I amplified the stratigraphic columns, and we can see how sedimentation goes through. First, in this stage, the plume doesn't affect the surface, so both columns sediment the same. Now, what we have is an interaction of the surface with the plume with the surface, and we have an uplift in column A. This creates an erosional or non-depositional environment in column A, but column B will still sediment. The next layer will only sediment in the far field, which creates, this is supposed to be not black. Probably that's some formatting issues. So what happens in here is that column A has a gap in time. There's no sedimentation of the bluish color, and this we call a hiatus. Finally, when the plume flattens and sedimentation resumes everywhere, column B has the expected sedimentation, and column A has a hiatus. So imagine that there's no black layer there. So what we did is extract these hiatuses recursively in the geological map. So what we can do is, how can we see these hiatus in the geological map? So if we have 3 layers, 1, 2, 3, and they are in a column, in the map view, we will only see the first layer. However, if they are a little bit shifted in the map view, we will see the contact between layer 1 and layer 2, and layer 2 and layer 3. And this would be the case of column B. Column A would be this also weird format, missing layer 2, which would mean that the map view will be, we will have a contact between layer 1 and layer 3. And this would create this unconformable contact. And if you can see that we actually assign different colors, conformable, it's going to be represented with blue, and unconformable is going to be represented with red. So now what we can do is a schematic geological map and see how do we map this. Okay, so we take layer T1 and we see where layer T1 is and what is in contact with. So in layer T1, if you see in here, layer T1 is in contact with T3. So these, we're going to map it as red. In here, layer T1 is in contact with T2, so this is going to be mapped as blue. And because we want to go to the extra mile and we want to define where there is a hiatus of the layer 2 and where there is not a hiatus of the layer 2, what we are going to do is map also the presence of layer 2 in the map. And if we do that systematically, we extract all the contexts available in the geological map. We get a bunch of time windows that indicate what happens to the previous time step. So in base of T1, which is duplicate here, we'll have that the layer T2 is not here, but it is present in here. Once we extract all these contexts, we will put it in a regularized grid and apply a spherical harmonic transformation. These will give us the following surfaces. These are what we call the base hiatus surfaces, or BHS. They are, in this case, centered in the South Atlantic. We have 8 time windows separated in geological time series. We choose the base of the Lower Cretaceous as our oldest time step because it corresponds to 1 transit time of the Earth mantle. Transit time is a time for a mantle overturn, and it's around 100 to 150 million years. So it's a geodynamic relevant time scale. Blue represents a no hiatus, and it means that the previous layer is there. So for example, if we take the base of the lower Cretaceous, blue is showing where the upper Cretaceous is. Red represents a hiatus, and it means that the previous layer is not there. We take again the base of the lower Cretaceous, we'll see that red is representing where there is not Upper Jurassic. And white is the absence of the series and the previous series. So when you see white in here, it means that there is no lower Cretaceous nor Upper Jurassic. The black dots that you see in here are the current location of the Iceland, Canary, Tristan, and Afar plumes. These maps we take these maps as a proxy of vertical motion that the area has undergone. So in other words, it's an indication of the topography of the preceding series. And they are a key result, and hopefully they will have a significant impact on the development of geodynamics in the future. The main observation that we see is that the proxy of vertical motion ceases to systematically change at timescales of geological series, which is around tens of millions of years. And note that this is significantly shorter than the mantle transit time, which would be the time expected for mantle convection dynamic topography changes. From a geodynamicist point of view, this gives us a clear indication of what are the properties, some properties of the Earth mantle. So if we look now at what the maps tell us, what we can see is that in Africa and South America, in the base of the lower Cretaceous, they are mainly, they have a hiatus. And this indicates high topography of the Upper Jurassic. Note that this uplift of the surface precedes the arrival of Tristan at 133 million years ago. In the base of the Upper Cretaceous, we have the context mainly conformable, and this indicates relatively lower elevation. As we continue looking forward, we see that the main hiatus surface that we see is at the base of the Miocene. But I am a global geodynamicist, so what we did is extract for all the continents possible. So here we have it for America, Europe, Africa, and Australia. And what we can see in these maps overall is that they also systematically change. Each map looks different, and each continent has a different evolution. We can, for example, focus in Europe. And if we look at the base of the Eocene in Europe, what we see is that there's also a hiatus surface. And this, again, precedes the arrival of the Iceland plume at 56 million years ago. And since we are in Australia, we can also take a look in Australia, and we can see, for example, in the base of the Eocene, that the continent is tilted. We have a proxy for subsidence in the east and a high proxy of dynamic topography in the west. But if you remember at the beginning of my talk, I told you about this wet wasn't flow, and I told you that there's a relationship between the vertical motion and the horizontal. So what we can do now is compare both observables, the base hiatus maps and the spreading rates together. So let's go back to the South Atlantic, and it's complicated slide. Let me just walk you through it. So at the beginning, I showed you the bimodal spreading rates of the South Atlantic, which now they are here in the lower row. Also, I explained you a couple of minutes ago the base hiatus maps, which, if you remember, blue means no hiatus and red means hiatus. And we take this as a proxy of high or low topography. But these maps are quite qualitative. So what we can do is extract a quantitative measure of how, of a measure of elevated areas. So we can do that, and this is presented here, extracting the aerial extent of hiatus and no information in the maps, and normalize it by the size of the continent, normalize it by the size of the continent. And this gives us these curves. For, in this case, it's Africa and South America. Africa is the continuous line and South America is the dotted line. And if we analyze them, we see that they are high for the Upper Jurassic, and then in the lower Cretaceous, they subside. In the Paleocene, the curves starts to differ, and it shows an uplift of South America. In geodynamics, it is often believed that South America has subsided over the last 100 million years from a high topography in Africa and then went down, but our maps indicate something different. Also, because Africa is a large continent, what we did is study it separately, the north and the south part. And what you can see here, the north is the dotted line, and the South Africa, it's the dashed line. If we look at these curves, we can see that there's a significant difference between the north and the southern part of the continent, with the southern part experiencing a major hiatus in the Upper Cretaceous. And this also coincides with numerous sedimentation studies. If we look now at the spreading rate variation, we can see that, so the model that I showed you before tells you that if there's a pulse of vertical motion, this has to create a lot of shear stress, which will result in a change in the spreading rates. And if we see that actually in here, in the Upper Jurassic, when we see a high pulse of elevation, shortly after, the rifting starts in the Lower Cretaceous. And we can also see it in the Paleocene, Eocene, Oligocene, where we have a high proxy elevation that coincides with the speed up of the spreading rate in the South Atlantic. This very time-dependent picture of the South Atlantic has been noticed by others, and there's a very good McGregor overview paper where they told us how the sediment flux in the sedimentary basin in the ocean changes. And there's actually an IODP report by Barker that shows subaerial exposure in the middle of the Atlantic at the Eocene, early Eocene time. But yeah, we can also look at Australia. And what the idea is the same. We also see variations in the hiatus maps. And the proxy elevation here that you can see is that the solid line is Australia as a whole. The dashed line we present, I present you the Western Australia, which coincides with the political map, and the rest we consider East Australia. And if we look at these, we can see that there's lower topography in the Lower Cretaceous, which increases during the Upper Cretaceous, and then East Australia drops, while Western Australia has a high proxy of topography. Then they both subside and have a high topography during the Oligocene. If we look at the spreading rates, what you can see in here is that the solid and the dashed line represent the spreading rates between Australia and Antarctica, and the dotted lines show the spreading rate in the low-how rise. And what we see is that when we have a high proxy of topography that coincides with the spreading rate in the east of the continent. And then when Western Australia is also high, has high topography, there's rifting starting in between the Antarctica and Australia. And this, we just submitted a paper that we associated with one of the plume, with one of the pulses of the Kerguelen plume. And I'm almost at the end of my talk, but what I wanted to show you is that I showed you all these wet puzzle flow models, and they were all in a linear form. So what we can do is actually study it in the sphere. So what we can get is the first, here you see the wet flow, which is an extraction from the plate velocities in the surface at 55 million years and 133 million years. Then we simulate the arrival of the flow that would be created if we have a plume entering the Asthenosphere in the locations of Iceland and Tristan. Here, what you see is the combined flow, which for some weird reason, there's no arrows anymore. And in Tristan, you also, well, here it's a combination between the wet and the frozen flow. And the main point of this slide is actually the fourth column. The fourth column in salmon orange color, you see the areas that are influenced by the frozen flow. So when the positive flow dominates the flow in the asthenosphere. And the blue one is if we consider the plume strength, half of what we did in here. And if we look at this, especially for Iceland, we can see that Iceland, either Europe is dominated by the impact of the Iceland plume arrival. And in the case of Tristan, we also have a significant impact in the surface. These areas that you see here are around 10 million kilometers squared, which is more or less the same that we obtained in the Hiatus maps that I showed you. But this is a very simple model, and what we can do is also go to much more complicated models, as I told you at the beginning. But having an observable of how dynamic topography changes through time allow us to constrain these models, these mantle convection models, and help us to define a little bit better the parameters that are unknown. It is also now to invert these models in time from the current state of the Earth to a sophisticated method that's called the adjoint. And the output of it is a trajectory of the past mantle flow. And actually that's the direction I'm heading now off. But so to finalize my talk, I just want to remark a few things. Dynamic topography is a crucial geodynamic observable. The base Hiatus surfaces are a proxy for dynamic topography, and what we saw is that they vary at time scale of geological series. This indicates a rapid upper mantle flow and is consistent with the presence of a weak asthenosphere. We see an uplift prior to the change of horizontal motion, which is linked to the size of the plume. And this is a disclaimer: geodynamicists need to embrace geological data sets in order to advance in our understanding of geodynamic processes in the deep earth. Thank you very much for listening.